All right, today we're going to dive into a story about a chemical family. We've got three pretty distinct relatives, all born from the same ancestor, and believe it or not, they're hiding in plain sight all around us. So, let's meet them.
Okay, let's kick things off with a little puzzle. I want you to think about, say, the wood polish you might use on a table, the antiseptic in your first aid kit, and maybe the scent of your favorite perfume. I mean, on the surface, they seem totally unrelated, right? But what if I told you they all share a common ancestor? See, the answer isn't a thing, it's a connection. All of these products, they get their most important properties from compounds that belong to one single family in organic chemistry. And to really get this family, you've got to understand how it was born in the first place.
And it all starts with something I like to call the oxygen makeover. We're going to start with a super basic, really stable molecule and just give it this tiny but totally life-changing tweak.
So meet the granddaddy of our story, the hydrocarbon. This stuff is basically the bedrock of organic chemistry, made of nothing but carbon and hydrogen. You can think of it as this simple, stable foundation, almost like a blank canvas, really, right before one little change makes everything a whole lot more interesting. Okay, so here's the key. It all boils down to one simple action. We take a hydrocarbon and we swap out one of its hydrogen atoms for a group that has an oxygen in it. And that single tiny change, it's like a chemical spark that creates a brand new compound with a completely different personality and a whole new job to do. Which brings us to our first and probably most famous member of the family, alcohols. Seriously, if this family had a job board, the alcohol would be that tireless, do-it-all workhorse. It does a little bit of everything. So what exactly makes an alcohol an alcohol? Well, it's all about this specific little attachment called a hydroxyl group, or just OH. When this group grabs onto a straight or a branching carbon chain, what chemists call an aliphatic system, boom, you've officially got yourself an alcohol.
And we're not talking about some obscure chemical you only find in a lab. This stuff is everywhere. The ethanol in wood polish, that's an alcohol. But get this, so are the basic structures that make up the sugar you eat, the cotton in your shirt, and even the paper you're writing on. Talk about versatile.
But, not all alcohols are the same. We can actually sort them out based on how crowded that main carbon atom is. Think of it like this. If the carbon that's holding the OH group is only attached to one other carbon, we call that a primary alcohol. If it's attached to two others, it's secondary. And if it's completely surrounded by three other carbons, well, that's a pretty crowded tertiary alcohol. And that crowding, it actually changes how they act.
Now, naming these things might look a little intimidating, but I promise it's just like following a recipe. Step 1, find the longest carbon chain that has that OH group in it. Step 2, take the basic alkane name, something like ethane. Step 3, you just swap the final E for an ol, so ethane becomes ethanol. Easy, right? And the last step is just to number the chain so that OH group gets the lowest possible number. It's a system that's designed to be logical, not to trick you.
All right, let's move on to the next relative, phenol. Now, if alcohol is the family's workhorse, you can think of phenol as the highly trained specialist. It's built for very specific jobs, all thanks to its unique structure.
So a phenol has that exact same OH group we just talked about. But here's the huge difference. Instead of being on a flexible chain, it's bolted directly onto a super stable carbon ring. We call that an aromatic system. Just picture this rigid flat hexagon of atoms. That one change, from a chain to a ring, changes absolutely everything.
And this right here just lays it all out perfectly. Alcohols have their OH group on a wiggly chain, which makes them super versatile. Phenols, on the other hand, have it on that rigid ring, making them specialists. That's why they're perfect for jobs like being a powerful antiseptic.
And wow, do they have a history. The original phenol, which also goes by carbolic acid, wasn't cooked up in some fancy lab. No way. It was first pulled out of gritty, messy coal tar way back in the 1800s. It's a great reminder that so many of our modern chemicals have these really humble industrial roots.
Okay, 136 picometers. I know, it might just look like a number, but this is the secret to phenol's power. That bond connecting the oxygen to the carbon ring, it's just 136 picometers long. So why should you care? Well, it's unusually short, which means it's unusually strong. It acts almost like a hybrid between a single and a double bond. And it's this incredible stability that makes phenol such a potent, reliable specialist for things like antiseptics. All right, time to meet our third and final family member, the ether. Now this one's a little different.
It isn't defined by some group hanging off the side. Instead, it plays the part of a quiet, stable bridge that connects two other parts together.
So the defining feature of an ether is pretty simple. It's an oxygen atom that's literally sandwiched between two carbon-based groups. You see it in the formula, R, O, R prime. Those R's can be chains, kind of like in alcohols, or they can be rings like we saw in phenols. But that oxygen in the middle, that's the bridge holding the whole thing together.
And classifying them is super simple. If the two groups on either side of that oxygen bridge are identical, the same thing on both sides, we call it a symmetrical ether. If they're different, well, you guessed it, it's an unsymmetrical ether. It's a really straightforward way to sort them out.
So what do these chemical bridges actually do in the real world? Well, they're the foundation for a ton of fragrances and perfumes. It's pretty amazing when you think about it, that this simple ROR structure is responsible for creating so many of the complex, beautiful scents we all enjoy every day.
Okay, so now that we've been introduced to everyone, let's bring them all back together for one final family portrait. It'll really help us see how they all fit into the big picture.
And this table just nails it. You've got the alcohol, our workhorse, with its OH on a chain showing up in everything from solvents to paper. Then there's the phenol, our specialist, with its OH on a ring, that's our key for antiseptics. And finally, the ether, our stable bridge, which is what gives us fragrances. 3 relatives, 3 totally different jobs.
So here's the big takeaway from all of this. All of this incredible diversity, from the stuff that cleans wounds, to the perfumes we wear, to the paper in a book, all of it comes from one simple tweak. A single oxygen makeover on a basic, boring old hydrocarbon.
And that really leaves us with one final, fascinating thought. If one tiny little atomic swap can create a family this diverse, this essential, it just makes you wonder, right? What other hidden chemical families are out there, hiding in plain sight in all the everyday things that surround us right now?